and so just to give you a brief introduction to the organizing committee, it's Abhishek, Jaskaran, myself, and Carl with Feria from IC Impacts' office. And as you can see, um, Jaskaran is from McGill, and all of us others, Abhishek, me, and Carl are from UBC. So it's a UBC McGill jointly hosted, student hosted event. So welcome to week 18 of the WESTalks. Today we have Dr. Treavor Boyer from Arizona State University going to give a talk on ion exchange and its applications for drinking water and wastewater treatment. And we have a lot of talks coming up as well. And if you have missed any of our talks, they are available on our YouTube page. So just to give a brief introduction of Dr. Boyer. So Dr. Boyer is an associate professor in the School of Sustainable Engineering and the Built Environment at Arizona State University. His research interests span water quality and treatment with numerous projects on innovative applications of ion exchange technology, particularly for emerging contaminants like perfluorinated compounds or PFAS. And he also works very closely in the area of nutrient recovery from source separated urine. Dr. Boyer is a recipient of the NSF Career Award entitled Sustainable Urine Processes Through Integration of Education and Research, also known as SUPER. And Dr. Boyer was previously an associate professor in the Department of Environmental Engineering at the University of Florida. So with this, I'll pass it on to Dr. Boyer. I'll stop sharing. And we welcome Dr. Boyer to our WESTalks. Thank you for accepting our invitation.
Great, thank you very much for the nice introduction. I'm really happy to attend. I know some of you through AWWA meetings, reviewing papers, so it's nice to be there. Just please let me know if there's any audio issues or anything. My dog gets a little crazy during Zoom meetings, so I may have to let her in the office here with me. Okay, so I'm excited to talk about the work I've been doing over the past around 10 years on ion exchange. And so I wanted to give kind of a perspective of what we've learned and what we're working on now. All right. I've had a lot in terms of funding, from the universities I've been part of, the University of Florida and ASU, different projects with the US EPA and important collaborators at universities and water utilities. I've had a lot of great students who've worked on ion exchange over the years. And so as you all know, this all research is possible through great students. And then also my advisor, Phil Singer, passed away this year. And so he's the person who, got me interested in ion exchange and natural organic matter. And so, I hope that's not seen him at conferences. So I started out, I'm start broad here with some slides just to get everybody oriented because I don't know everyone's background. So ion exchange, I have it both viewed here at the micro scale and the macro scale. So at the micro scale, it's a certain type of adsorption process. And it's an adsorption process that is, controlled by electrostatic interactions. And so here I show an anion exchange resin, some negatively charged contaminant exchanging with the mobile counterion chloride. At the macro scale, we have some kind of black box ion exchange process, some kind of reactor. And we have contaminants in and, ideally contaminant-free water out. I put a little asterisk there. I won't talk about it too much, well, to some extent, but you remove the contaminant and you thereby release the mobile counterion. And so it is important to think about what are the implications of releasing that counterion into the treated water. Regeneration is a key part of ion exchange, so unlike things like activated carbon or biochar, ion exchange resins are much more readily regenerable. And there you reverse the process, right? So you have a resin, an ion exchange resin with your contaminant X on it. And traditionally you would say expose it to a sodium chloride solution. The chloride would displace your contaminant. So now back to our macro scale in the reactor, sodium chloride in, still a lot of sodium chloride out, but your contaminant as well. And then how you manage this waste stream is a huge challenge. The reactors, those black boxes in the previous slides, typically, or historically, it's been a fixed bed reactor. However, there's a lot of research over the past 10 years on completely mixed flow reactors. One example is the NOM IX process, but there's been other suspended ion exchange processes that have been studied. Some innovations that we've pioneered and I'll talk about today. One is combined ion exchange. So a relatively simple idea that we have mixed contaminants in Florida and other places. You know, a common problem would be, say, high DOC and high hardness. And so instead of dealing with that with two separate processes, the idea is that combined ion exchange, combining anion exchange resin for DOC and cation exchange resin for calcium, you could remove these multiple contaminants in one simple process. Another innovation is bicarbonate-form IX exchange. And here I'm showing that the resin is being regenerated with, say, a sodium bicarbonate solution instead of sodium chloride. The idea here relates back to, first of all, during the contaminant removal phase, you're going to release bicarbonate into your treated water instead of chloride. So there's some benefits there in terms of creating a less corrosive water. And then the other idea is that your sort of final waste stream here is now, say, a sodium bicarbonate solution with contaminants instead of sodium chloride. And the premise is that that can be easier to dispose of. And then finally, our work has really taken a systems thinking approach. And so instead of just looking at one aspect of ion exchange, we really try to study the entire system, from contaminants to the treatment configuration to regeneration. And that, a big part of this systems thinking is things like doing regeneration with an alternative to sodium chloride. And I'll elaborate on all these points today. And so in terms of the outline for the talk, I'm going to progress from sort of thinking about species that we can remove by ion exchange to more about the resins, then expanding further to thinking about the system, and then finally some ideas for future work. So natural organic matter, I know some of you there are involved with natural organic matter. When I was at the University of Florida, and I would have to sometimes go to the panhandle part of the state, I would drive over the Suwannee River. So that picture there is from the Suwannee River. There's many conceptualizations of NOM. Here I have just a sort of classic idea of you have aromatic carbon and you have acid functional groups. The key thing for us in ion exchange, as shown in this figure, is its pH-dependent charge characteristics. And so during my PhD, I worked with a variety, as shown here in the legend, of natural organic matter isolates, and I characterized them in terms of their charge density, which is a critical property for ion exchange. And so this was what came out of that work, and it was very important in that what I was able to show here for really the first time was that natural organic matter, although it's this complex organic compound, is removed by stoichiometric ion exchange. And so that's shown here by, on the x-axis, looking at the net uptake of bicarbonate and DOC. So these test waters had different types of organic matter isolates, as shown by the legend, and some bicarbonate buffer, and then measuring the net chloride release. And you see a very nice one-to-one relationship between the uptake of bicarbonate and DOC and the release of chloride. And this is possible through characterizing those charge characteristics of the NOM. Then looking at the selectivity, we all know, or those who work with NOM know, that it varies based on sort of external and internal processes. How is the NOM sort of further processed in the watershed? And what we see here, which is interesting, so the x-axis is the equivalent fraction in solution, and the y-axis is the equivalent fraction in the resin. This is a common way to present sort of ion exchange adsorption isotherms. And again, I had this array of different organic matter fractions, and they're kind of bounded between sulfate, which are the blue circles, and then nitrate and bromide, which are the squares and the triangles. And depending on the characteristics of the NOM, like things like its aromatic carbon content, or molecular weight, some of the fractions were say as selective as sulfate, other fractions were less selective. And so that's important, and those who work in NOM research have recognized the importance of those characteristics. I expanded this work, so a lot of my early work was with the magnetic ion exchange resin, which in some cases has some unique properties, but in other cases is really just a polyacrylic strong base resin. And so worked with the Suwannee River fulvic acid that many researchers work with because of its well-characterized properties. showing that same type of plot of bicarbonate and DOC uptake by the resin and chloride release. Now looking at a variety of resins from different companies that span both polyacrylic and polystyrene composition, all of them exhibiting the same ion exchange behavior. When we look at where the resin properties do differ, it would be in terms of the actual amount of DOC removed. So here on the x-axis, I have resin dose expressed as milliequivalents per liter, and that is because different resins have different ion exchange capacities. So now we're comparing the resins on an equivalent capacity basis. We're looking at the normalized DOC concentration. So the lower the normalized DOC concentration, the more removal. And we really see sort of two sets of data. We see this data here. Hopefully you see my cursor with the triangles, diamonds, and squares, meaning high removal of DOC, low normalized concentration. And then we see the star and the circle data up above. And so the high removal corresponds to polyacrylic resins, and the less effective removal is polystyrene resins. These things are well understood now, but this was some of the first work to really conclusively show that. And so in terms of current research, where we are going, and you know, I take note of what other researchers, especially those at UBC and in Canada, are doing with NOM. And I'm really intrigued by the biologically enhanced ion exchange that some of you have been looking at. And so we've been studying that as well. And so in this figure, we have bed volumes treated. And this was about a 9-month study. It actually did get a bit cut short by the coronavirus and sort of having to ramp down lab activities. The black circles, either solid or open circles, are chemically regenerated data, like every 10,000 bed volumes, or excuse me, I can't remember how many bed volumes exactly, every several thousand bed volumes. And then the triangles are the not allowing for regeneration. So doing this sort of letting the biological processes take over. And we've seen what others have observed, which is, you get this sort of plateau of around sort of a sustained 50% DOC removal, the triangles, even though you're not chemically regenerating. And we were able to dig deeper into that, as shown here, which is, how are the ion exchange sites occupied? And what we see is in the upper figures here, although it's a little confusing, the black is chloride, the red is sulfate, and that green is DOC. The upper columns 1 and 2 are chloride regenerated. And so we see the sites, they alternate between being occupied by chloride and being occupied by sulfate predominantly, because DOC has such low charge density. However, in columns 3 and 4, where we let the biological activity take over, although there is very apparent biological activity, what we actually see is the secondary ion exchange phenomenon, that initially the resin is occupied by chloride. However, over time, the resin sites become occupied with sulfate. And then it's those selective fractions of DOC that I mentioned earlier, some of those fractions are more selective than sulfate, are actually exchanging with the sulfate-form resin and allowing continued, say 50% DOC removal. Where we're going with this next is thinking about contaminants beyond NOM. So for example, using sort of biologically enhanced ion exchange in a nutrient removal context to do things like denitrification. And I'm happy to talk more about that. We have some interesting preliminary data. And so now let's move from NOM to PFAS, which is a compound that many of us are interested in. I have just 2 of the most common, PFOS and PFOA. In some respects, kind of similar to NOM, right? We have this sort of hydrocarbon structure. In this case, though, it's perfluorinated, so it is quite a bit different. But then we have these acid functional groups. So PFOS, PFOA, the other perfluoroalkyl acids act as anions. And so we would expect ion exchange to be an effective process. I did want to sort of just show this slide to remind us that, because the PFOS and PFOA are surfactants, there is a wider range of sort of adsorption processes available. I mean, the electrostatic attraction and repulsion is still likely. However, there's possibilities for things like hemimicelle and micelle formation within the pore water, which can really complicate the ion exchange process. And so this is some recent work that we've completed looking at the interactions of NOM and PFAS during ion exchange. To orient you on these figures, on the x-axis, we're looking at either chloride-form resin or sulfate-form resin. I'm going to ignore the sulfate-form results for now and come back to that in a little bit. And so then up above, we have looking at DOC removal in the absence of PFAS and in the presence of PFAS, and comparing two resins, A520E, which is a polystyrene resin, and A860, which is a polyacrylic resin. And if you just take some quick glances at these figures here on the left, what you see is that DOC removal is greater by the A860 resin, the polyacrylic resin, than the polystyrene resin. And that's an expected result based on what I showed in my PhD work and what others have shown. And that PFAS really isn't interfering with the DOC removal, which in general, since the NOM is present at a couple orders of magnitude higher concentration. Now, if we flip this and look at the PFAS removal, first on the polystyrene resin, and so now we have, focusing on the left, we have the chloride form polystyrene resin, looking at 6 of the PFAS, as shown here in the legend. First, with the absence of NOM, and then the presence of NOM, and all the NOM work I should mention is Swanee River NOM. Looking here, what we can say is we see trends that others have seen, which is the sulfonate PFAS are removed to a greater extent than the carboxylate PFAS. You can see that with the sort of blue shaded bars being lower than the gray shaded bars. And not really an impact of NOM, which is a bit interesting. There's been sort of a variety of results on this, or, to what extent does NOM impact PFAS removal? I guess what I would say here is that we're using in these results a polystyrene resin. Polystyrene resins are less selective for NOM. So for me, it makes sense that this polystyrene resin is effective for PFAS and not really showing any interference by NOM. We then hop over to a polyacrylic resin looking at PFAS removal, showing the results the exact same way. And a couple big takeaways would be, first, much less removal of the PFAS by the polyacrylic resin than the polystyrene resin. And it's really unclear what the impact of NOM is because there's much less PFAA removal. And so maybe I'll stop. So here then, just to kind of quickly come out of the stop share mode for a second, what we've seen is, the importance of resin properties and their interaction with contaminants. For example, a polyacrylic resin more effective for NOM, a polystyrene resin more effective for PFAS. And then what we want to think about is, well, what about all the other resins, or excuse me, all the other contaminants that are possible? And so that then leads into our sort of really trying to understand, multi-contaminants and the role of combined ion exchange. So we've talked about NOM and PFAS. There's situations where you might have NOM and or PFAS combined with inorganic anions or metal cations. And so let me explore this topic a bit. And so our original approach to this was really very applied, and that was this idea of utilities needing to remove multiple contaminants. And for us, that sort of combination was DOC and hardness, calcium and magnesium hardness. And so what we looked at was simply 2 different magnetic ion exchange resins, the magnetic anion exchange resin that most people are used to and refer to as MIX, but the company had also created a magnetic cation exchange resin. Just one second. Sandy. My dog. And so here with the cation exchange resin, what was surprising was, not only did it remove hardness, but it removed some of the organic matter, some of the DOC and UB254. Of course, the anion exchange resin, almost exclusively removed the DOC and not any of the hardness. And then when we combined, the 2 resins together, it seemed additive. an interesting result that we wanted to explore further. And really we wanted to think in the context of, well, what could be in this groundwater? And so you could have situations where you have the, the natural organic matter, but then we wanted to expand that to the whole sort of, alkaline earth series. So calcium, magnesium, strontium, barium, because those can be relevant in some groundwaters. They can be relevant if we're thinking about things like membrane concentrate. And then we had to, acknowledge the unique characteristics of the MyX resin. I said in some cases it's just another polyacrylic resin. However, it does have this, magnetic iron oxide component. And so there is now really quite a wide range of possible interactions. You can have complexation between the metal cations and the DOM. That could further, have some complexation with the iron oxide in the resin. You can have the simple cation exchange with the cation. So we really wanted to try and unravel, from the from the results on the left to the sort of the resin on the right, we wanted to unravel what was happening. And so the way we approached that, this figure's a little busy, but let me help you with it. So first, on the x-axis, we altered the counter ion of the resin. So this would be the magnetic cation exchange resin. We used it in the sodium form, magnesium, calcium, strontium, and barium forms. Then we looked at DOC removal here on the y-axis in the presence of calcium and magnesium, magnesium alone, and sodium. So the idea of possible complexation between the metal cation and DOC and no complexation. And so when you look at these results, what you see is that when sodium is in solution, when sodium is the counter ion, you get maybe still 20% DOC removal, which is odd for a cation exchange resin. However, as you add divalent cations to solution, or as you have divalent cations on the counter ion, you see increased DOC removal. So that tells us that there is, DOC complexing with the resin or adsorbing to the resin. It tells us that there's, DOC cation interactions that are then undergoing ion exchange. Because of this, we realize that the combined ion exchange process really needs to be done with then just a conventional cation exchange resin. And so that's what we then pursued, was using the MyX resin for DOC removal, and then using a traditional cation exchange resin for hardness removal. Here, what we're doing is, looking at a real groundwater, doing the sort of multiple loading jar test approach for bed volumes, and trying to understand things like regeneration. Because, what happens when you try to do this combined ion exchange is, the DOC and calcium are present at sort of orders of magnitude different concentration in terms of milliequivalents per liter. And so, finding sort of effective ratios of anion exchange resin to cation exchange resin is challenging. Sort of tailoring the regeneration process is challenging. So that's some of the work we've done on combined ion exchange. Let me say a few things about advancing bicarbonate-form ion exchange. I'll focus first on the process performance of bicarbonate-form ion exchange, with the idea that one of the motivations is sort of the downstream impacts, but also thinking about the upstream environmental impacts as well. And so early on, what we wanted to do, and as I've said, we used MyX resin in a lot of our earlier work. We've now kind of moved to other sort of non-magnetic resins. In many cases, the results are the same. You just have to know when to understand, how the MyX resin might be different. So here, making a comparison of bicarbonate form resin with chloride form resin, looking at the resin performance over multiple regeneration cycles, and then looking at both DOC, and UV absorbance, sulfate, nitrate. And what we saw was that, in an ion exchange selectivity sequence, resins have a very low selectivity for chloride, and they have an equally low selectivity for bicarbonate. And so what we've found from our work is that, replacing chloride with bicarbonate really has very little impact on contaminant removal because it has that low selectivity, and that you're still able to get some effective regeneration. The challenge with sodium bicarbonate is that its maximum solubility is around 8%, whereas sodium chloride can have a much higher solubility. And so, sometimes your regeneration is a bit constrained by the solubility of sodium bicarbonate. So this was, just several regeneration cycles. We wanted to extend this over a year of regeneration cycles. So this was 21 regeneration cycles, essentially taking a batch of resin, doing a jar test, regenerating it every other week with do a jar test with water, regenerate it, repeat. This was a river source. And so what we see here is, some of you who do NOM work will find this pretty amazing. I mean, this is a surface water river that has DOC that varies between 25 and 15 milligrams per liter, an incredible amount of DOC in the surface water. We're comparing the bicarbonate and chloride-form resin, and we see really, quite very similar performance for DOC removal. So showing that the bicarbonate resin can be, effectively regenerated over a long process. This source had quite high bromide, on the order of 500 micrograms per liter. It does vary in the source. And, bromide is a bit trickier to remove by ion exchange, especially by a polyacrylic resin. But we see pretty effective removal. And at least, we see similar removal between the bicarbonate and the chloride. There was some thought that maybe the bicarbonate resin could be more effective for bromide, but we didn't quite see that. Here now I wanted to just include as a segue into the sulfate-form ion exchange work. And we had been focused on the bicarbonate-form ion exchange for two reasons. To make the treated water less corrosive, that is, we're adding bicarbonate to the treated water instead of chloride, and to provide other opportunities for the waste regeneration solution. The idea is that you have an alkaline waste regeneration solution with bicarbonate that should have more disposal options than a chloride. Now we took a similar sort of rationale for looking at sulfate-form resin. And that is, for the PFAS process, the idea is that the sulfate brine, which contains PFAS, would be more amenable to oxidation processes to destroy the PFAS than the chloride form. When you try to do advanced oxidation in a chloride brine, you have the risk of forming perchlorate. Whereas in a sulfate brine, the idea is that you could even create sulfate radicals that could help destroy the PFAS. And so importantly, here with here are the DOC results. What we saw was that when especially the A520E resin was put in the sulfate form, it performed more effectively, if you look across these figures, than the chloride form resin in terms of DOC removal. And that's the same, these upper figures are without PFAS, with PFAS. So really interesting that the sulfate form resin performed better. It's interesting because resins have a high selectivity for sulfate. We then look at the PFAS results for the A520E resin, and we see pretty much the same thing, that for this A520E resin, when we put it in the sulfate form, we get more effective removal than the chloride form. When we look at the A860 resin, we really don't see an impact of the sulfate relative to the chloride. And so when we step back and think about this, the A520E resin has some unique properties in terms of its functional groups. Those functional groups are intended to be selective for monovalent ions instead of divalent ions. And so the idea that we need to look into further is that by putting this sort of monovalent selective resin in the sulfate form, we're really putting it in an unfavorable state. And that's why it's able to more effectively remove contaminants in the chloride form. And then again, this is promising because we do the regeneration with the sulfate. We now have PFAS and sulfate, and so we can pursue some electrochemical processes to destroy the PFAS. So that was a little segue into the sulfate to say a few more things about the bicarbonate form, where we've done quite a bit of work, which is, this is a new ion exchange process. And so we had to establish new selectivity data, for example. And so a PhD student looked at a range of inorganic contaminants like perchlorate, chromate, nitrate, bromide, and a range of resins. And some of you who do ion exchange will recognize these are, this is a polystyrene resin with a triethyl functional group. We have a polyacrylic resin with a trimethyl group. And what we were able to do was establish selectivity sequences for perchlorate, chromate, nitrate, sulfate, bromide based on the resin properties. And we're able to explain these based on things like the polymer composition and the functional group chemistry. All of this is trying to, help water treatment plants, advance water treatment. And so we moved on then to fixed bed ion exchange pilot plant. And so this was a long-term study out at a water utility comparing chloride-form resin with sulfate-form resin, and comparing both polyacrylic and polystyrene. So here in test one, we have the polyacrylic resin. We're using 16% sodium chloride for regeneration, 8% sodium bicarbonate. So here you can see the raw water, DOC between 5 and 6. Here you can see the orange or red is the chloride effluent from the chloride column. The black is from the bicarbonate. Really very similar performance over these multiple regeneration cycles. And then we repeated that work with a polystyrene resin. And again, pretty similar results. This was, over several months, and so the raw water was changing. But as we had seen at the batch, but now really validated at a fairly large scale pilot, that the sodium bicarbonate, even limited to that 8% salt solution, is able to effectively desorb the NOM and allow for multiple regeneration cycles. So my student Elise spent some time thinking about sort of broader comparisons, and so if we go through this figure starting in the red section, really DOC removal was the same, whether it was sodium chloride or sodium bicarbonate regeneration, or DOC removal was the same regardless of the counter ion. There was slightly better regeneration efficiency if you actually crunch the numbers and do a mass balance with sodium chloride versus sodium bicarbonate, given that you can have a higher sodium chloride concentration, but bicarbonate still worked well. The polyacrylic resin was more easily regenerated than the polystyrene. In terms of disposal costs, dealing with the sodium chloride waste was more expensive than the bicarbonate, and that's because the sodium chloride waste has to be disposed of by deep well injection, whereas the sodium bicarbonate waste can be discharged to the sewer to provide alkalinity. But the trick here is that in terms of chemical costs, sodium chloride is a very inexpensive chemical. Anything you want to use other than sodium chloride is going to be more expensive, so that's a challenge. We repeated that work instead of using a fixed bed pilot, now a completely mixed flow reactor pilot, set up at the same site there where the sort of resin is continuously mixed and recycled. My student created a model of that process, and importantly, that model was able to respond to different regeneration solutions, either sodium chloride or sodium bicarbonate, and respond to the different concentration of salt. And so here, these are different, as you can see in orange, different actual pilot plant tests and model predictions. And model predictions were usually within, 10 or 20%. And so we then have a model that can help us, understand, well, what is the impact of changing the regenerant from sodium chloride to sodium bicarbonate? What is the impact of changing the concentration of the regenerant? We then use that pilot plant to sort of expand our, so now we're sort of trying to link the work we've done on combined ion exchange with the bicarbonate-form ion exchange. And so in particular, so here on the left, we have DOC removal, looking at it over multiple regeneration cycles, in one case with a chloride-form resin in orange, another case with a bicarbonate-form resin in blue. But we're also doing combined ion exchange. So we have just a traditional cation exchange resin there, removing calcium. And the way it works is that we paired it with either a sodium form resin or a potassium form resin. And so what we see is that really between bicarbonate and chloride, similar DOC removal, between potassium and sodium, similar calcium removal. And so now that allows us to think about, well, what salt makes the most sense for regeneration? Is it sodium chloride? Is it potassium chloride? Is it sodium bicarbonate? Is it potassium bicarbonate? Really, sodium chloride is the most kind of detrimental to the environment. However, it's the cheapest. And so how do we balance those impacts? Here, just expanding to even more contaminants. So, instead of just one anion and one cation, we can have DOC and nitrate. We can have calcium and strontium. And the real take home here is that if you're going to go after multiple contaminants, you need to think about the resin properties. We were using a DOC selective resin, so it's got, poor nitrate removal. The cation exchange resin performs pretty similar for the alkaline earth metals. So this relates to what I had mentioned about the different sources of regenerant chemicals. So sodium chloride in the legend here at the top, potassium chloride, sodium bicarbonate, potassium bicarbonate. And then this is looking at the environmental impacts through a life cycle assessment study. And so what it turns out is that potassium bicarbonate has the highest environmental impacts. And both, typically sodium chloride has the lowest environmental impacts. However, sodium bicarbonate can also have low environmental impacts. This comes from the fact that, some of these chemicals are sort of naturally occurring, like rock salt, and there are natural deposits of potassium chloride and sodium bicarbonate. But something like potassium bicarbonate has to be further produced from things like potassium hydroxide and CO2. And so that's why the higher environmental impacts. So this is the sort of upstream impacts of a regenerant. Downstream, where do we dispose of it? Well, it's possible that we could dispose of regeneration solution to fresh water. It's possible we could dispose of it to soil, through a spray field, or discharge to a wastewater plant. When you look through when you think about the composition of the waste streams, obviously disposal to fresh water doesn't make sense for any of these salts. To soil, depending on what your contaminant is, if it's something just like NOM, KCl is pretty favorable for soil. That's essentially potash, which is applied to soil in agriculture. In wastewater, again, you don't want to discharge a hazardous chemical to the wastewater, but from the bicarbonate point of view, you're providing alkalinity for things like denitrification. And so sometimes I like to stop here just to kind of refresh everyone. I have probably maybe 5 more minutes to wrap up here. So I've talked about drinking water applications of ion exchange, which has been a large part of our work, but also wastewater applications are equally kind of interesting and important. And that's because, we're all familiar with the idea of the urban water cycle, where, on this half, the right half is our sort of drinking water treatment side. And then over here on the left half is our wastewater treatment side. Well, for me, wastewater treatment is urine diversion. And we can get into this more, but it's the idea that the composition of wastewater, the design of wastewater treatment plants is really strongly influenced by urine. Urine contributes the majority of nitrogen and phosphorus to wastewater, and much of wastewater treatment is around nutrient removal. So if we separate urine, we can recover nutrients. We can use less water because we actually want to separate undiluted urine or just barely diluted urine. It can make wastewater treatment more effective because there's less nutrients going to the wastewater plant. And many of the pharmaceuticals we take, the hormones we excrete are in urine, so it gives us a concentrated waste stream to target those. We've done a lot of work on that process of urine diversion in terms of urine collection, pharmaceutical removal, nutrient recovery, life cycle impacts, and even getting into user opinions. Here, I just want to present a few slides on our vision for pharmaceutical removal and nutrient recovery. So the idea is that you collect urine, and then you'd want to process it through, say, an adsorption or ion exchange column for pharmaceuticals first. You could then recover the phosphate second through selective ion exchange, and you could recover the ammonium and potassium third, again, through some selective cation exchange. I'm going to just present a few results on pharmaceuticals. And so we started out with a pharmaceutical Diclofenac, which is shown over here. It has aromatic structures. It has a carboxylic acid group. And what we found here on the left was that the polyacrylic resin showed very low removal of diclofenac, but polystyrene resins were very effective. And what that suggested to us was that, the electrostatic interactions are important. It is negatively charged. However, the non-electrostatic interactions were also important in adding selectivity. We then expanded that work to other pharmaceuticals, ibuprofen, ketoprofen, naproxen, and importantly, we did that at realistic concentrations. And we were able to gain insights into the selectivity of anion exchange resin for and these were chosen, these pharmaceuticals, because they're widely consumed, some of the most widely used pharmaceuticals in the world. So that means they're very prevalent in wastewater. And so we were able then, as shown at the bottom here, establish a selectivity sequence based on the combination of both electrostatic and non-electrostatic interactions. We continue to kind of push this work. And so one thing as well, when you take a medicine, you excrete its active ingredient, but you also excrete a range of metabolites. And there we start to run into some challenges. I'll just highlight this figure here in the red, where we have the triangles are just removing diclofenac from a sort of synthetic urine. The open circles are when we add metabolites to the synthetic urine, and the solid circles are when we use real urine. And this is C over C0, so we're seeing less and less removal. And that's because we're having more and more competition for ion exchange sites. So that's a real challenge. We can get selective removal in a cleaner system, but when we move to a more realistic system with metabolites and other organic acids, it's much more challenging. Something we've tried to think about is moving away from just mass removal or percent removal and thinking about why are we trying to remove these contaminants. With things like pharmaceuticals, it's because they are biologically active and have a toxicity endpoint. And so here in this work, one. Very sorry, the challenges of working from home. And so here we're trying to think about toxicity removal and contaminant removal. And how do we design a system? Do we design it for targeting 90% removal, or do we really think about the toxicity endpoint? And where these results come into play is when we think about the overall system. And so I think this is my last slide, which is looking at the life cycle impacts of doing ion exchange for urine treatment versus making upgrades to a wastewater plant. So A is a conventional wastewater plant. B is a wastewater plant with ozone. And then C through H are different ion exchange configurations for urine treatment. And so what we can see is that the conventional wastewater treatment plant has a high toxicity kind of impact on the environment. Ozone has the lowest, but just by doing the urine separation for targeting the pharmaceuticals, we can get much more of a toxicity reduction than the current wastewater plant. All right, so to wrap up, starting from sort of this figure here of species, we've done work on NOM and PFAS and pharmaceuticals, inorganic anions, metal cations, ammonium. Really, what I wanted to show with this list was the versatility of ion exchange in terms of inorganics and organics, anions and cations. In terms of the resin, we see a lot of advantages to thinking about the counter-ion form to get beyond just chloride. There can be advantages to using bicarbonate. There can be advantages to using sulfate. Combining resins also is simple, but it can result in effective processes, removing multi-contaminants. At the system level, we've done work on life cycle assessment to really understand where are the parts of the process that have the greatest environmental impact and how can we kind of reduce those. Where I see ion exchange fitting into drinking water and wastewater systems of the future is really in a distributed manner, so not fully decentralized, but a mix of decentralized and centralized. I'm interested in pursuing more work on, coupling ion exchange with destruction so that we can ultimately get rid of that contaminant. And again, just kind of extending this future work, multi-contaminant removal is attractive. A lot of today's talk was on contaminants, right? But resource recovery is another major advantage of ion exchange. And then, as some of you at UBC are familiar with, this idea of biologically enhanced ion exchange, and looking at that beyond NOM. So I appreciate the opportunity to present there, and I'm happy to answer any questions.